Okay, so hello students. We will talk about a new material today, and namely counting. This do you see the slides? I think you should be seeing a slide right now. Let me change the pointer. Okay, so we are entering the last segment of the class on counting or combinatorics, and it's all it's all in the I'm trying to make it make it so that I can see the chat. Well, okay, so I assume that if people ask some other questions on the chat, then maybe everybody else can answer, or a TA can come. Other than that, I will just answer these things at the end of the class. I don't know if this chat stuff is done in a way that you guys can type in and broadcast to everybody else. Yeah, right? Because if you can see a question that other people ask, so you can provide an answer. All right, good. Okay, so counting is the new segment of topics, and we'll see how far we get. First few sections of chapter 10. Okay, well, we start with something called the product rule. So basically, all we're going to talk about is how to count cardinality of sets. Well, it should be simple, right? I give you a set and you can count its cardinality. But when I define a set in some particular way, you might have trouble like, well, how do I count all elements in this set? If a set is tiny, you can draw them, and count them by hand. But if a set is a large set, for some sets it seems easy to count them, and for others you have to think a little bit. And the more we go, the more thinking you have to do, basically, right? And there are some rules and some methods in this, and this is all we are talking about. Okay, so the product rule basically allows you to count sequences, cardinality of sets of sequences. So let's start with an example. Let's say a lunch is defined by selection of three things: a sandwich, a side, and a drink. Okay, so a lunch selection means you choose a sandwich, you choose a side, and you choose a drink. And now you're asked, okay, how many lunch selections are there? Okay, so a lunch selection is a triple. It's a sequence. First is the sandwich selection, second is the side selection, and a third is the drink selection. So an example of a lunch selection is burger, fries, Coke, right? How many lunch selections are there? Well, it's as many as there are sequences whose first element is in this set of sandwiches. So one of burger, grilled chicken, grilled cheese. The second element is an element of size. So it's one of fruits or fruit. And the third is an element of this set. It's one of those three. So how big is the set of such triples? Well, it's the number of possibilities for the first one times the number for the second element times the number for the third. Okay. So there is 24 possible lunch selections. In general, the idea is this. So suppose you have some sets A1 to AN, and what you're really asking is how big is the set of all sequences whose first element is in A1, second in A2, etc. Okay, so what is this set? This is the set of sequences of n elements whose first element is in here, second in here, etc. And what's the cardinality of such set? It's the cardinality of the first one multiplied by cardinality of the second, right? You just multiply cardinalities of these component sets of the Cartesian product, right?
These are a number of elements in set, right? Like the total set, right? Like everything, all elements, right?
The vertical bars is cardinality of a set. So whatever A1 is a set. This denotes cardinality of it. So the number of elements of it. So the product rule is basically, well, you're told some selection. So for example, a lunch selection is a sequence of elements in that case, 3 sets, A1, A2, A3. You have to choose something in A1, that was your main dish, something in A2, that was your drink, and something in A3, or whatever, a side, I forget, right? So, but you have to do 3 choices. Now, these 3 choices were also independent, right? It didn't matter, like whatever main dish you choose, you were free to choose any drink on any side, and vice versa, right? So the choices are independent. And basically, you can think of this process of choosing something in the set as making 3 choices one by one, and independently so. Okay, and at every time you can draw it basically as a tree. At the beginning, there's 3 possibilities for the main dish. In the next level, there's 2 possibilities for what was it? Side. And at the end, there's 3 possibilities of drinks. And now the question is, how big is this tree? I mean, how many leaves does it have? How many ways can you go from the top to the bottom? And it's going to be this multiplication, right? Because basically the number of forkings is the size of the first set on the first level. The number of forks on the second level is this. And the number of forks on each consecutive level, right, is the cardinality of the corresponding set. That's why you just multiply them to see all the possibilities, right? Because every path in this tree corresponds to a unique sequence in here, to a unique sequence like this. So in this previous example, a unique lunch selection. Okay, so here is another example. Suppose you have an elementary school, has 5 classes, 5 grades, right? And a student council must have, it's a selection of students that has exactly 1 from each grade. Okay, so let's say CI is the number of, is the set of students in class I. So C1 is students in grade 1, C2 is students in grade 2, etc. So how many student councils do you have? Possible student councils do you have, right? And it's the product rule, because a student council is a sequence whose first element is in C1, second in C2, third in C3, etc. And so student council selection is this type of student 1 must be in class 1, student 2 in class 2, etc. Right? And well, so how many such sequences are there? As many as elements in this set. But you know how many elements are in this set. Cardinality of this whole Cartesian product is just the cardinality of each of these individual sets multiplied, right? Okay. Yeah, so ask a question if there's something not clear in what I'm saying. Okay. Here's another example. So say you have an athlete whose exercise schedule for a week means what they are going to do in the 7 days of the week, right? So she can each day, she can either run, swim, or bike. There's 3 choices. And how many exercise schedules are possible? You know, how many exercise schedules are there? So what are these exercise schedules, right? Each schedule is a sequence So C is the underlying set, right? Like the possibilities for every day, it's the same set: run, swim, or bike. And unlike this example, where the set of students in this class is different from the set of students in the other, right? So the first student must be in this set, the second in this set, and the two sets are different. Now it is a cardinality, but every set is the same. The exercise choice on the first day is from set C. Exercise choice on the second day is also from set C. Every day you're choosing an exercise from set C. So how many schedules there are? What are schedules? Schedules are sequences of 7 elements, each of which in set C. So this is the set of schedules. And its cardinality is the cardinality of C to the 7th power. So it's 3 to the 7th. Okay. It's the same thing, except that the set happens to be the same for every characters you choose. It's chosen from the same set, but the characters are chosen independently. It doesn't matter whether you swam in the past. You know, when you choose what are you doing on the 6th day, you don't care what you have done on the previous 5 or what you are going to do on the 7th. Every choice is possible, right? Okay, so say a school cook has 30 possible meals, and there's 20 school days in a month, right? What is all possible lunch schedules? So what is a lunch schedule? It's a choice of lunch for each of the 20 days. Each day is independent. So I'm going to call a schedule different if it has, you know, I don't know, beefsteak on the first day and you know, lo mein on the second versus lo mein on the first and beefsteak on the second, right? The order matters. And every day you're choosing one out of the 30 possibilities. So sadly, I don't have, yeah, so people will say D, okay, and that's right? So because this is the one, because you have a lunch schedule is a sequence of 20 elements, and each element is chosen in this set of 30. So each one is chosen out of 30 each, right? So there's 30 choices in the first day, 30 on the second, 30 on the third, and so forth, 20 times. So this is the total number of choices. This is also the cardinality of strings, set of strings who have 20 elements, and each of the elements is in the alphabet that has 30 symbols, right? Each symbol designates a different type of lunch. Okay. Okay, sorry, I forgot that I had this enumerated here, and I should have flashed it earlier. So C to the N is all possible lunches. It's a set, and this is the cardinality of that set, right? Where C is the number of, is the set of meals. There's 30 different meals. Okay, let's give some examples from domain of string counting. Okay. Okay, so the basic thing, like how to count strings, right? Like, so this you last week when we did conversions between different counting systems, right? Binary to decimal, hex, etc. You dealt with strings of n characters over some alphabet. So, for example, decimal digits, or bits, or hex digits, right? And if you just ask, okay, how many? If you're restricted to n digits, in this alphabet, how many possibilities you have, this map, all right? Because there is cardinality of sigma, it's the number of choices for each character, and there is nth characters. Okay, or you can think of this as a selection process. So for example, how many binary strings of length 4, right? The alphabet has 2 elements, there's 4 characters, it's 2 to the 4th. Okay, so 16, and by the way, this is also the number of possible, if you have only 4 bits, what are the binary strings, what are the numbers that you can, what is the highest integer, what are the integers that you can represent from 0 to 15? So 16 different integers, and that's because there's only 16 such strings. Okay. Okay, here's a way of counting of different thing. Then if you want to count not sequences, but elements of sets, which is a union of a given set. So you have a bunch of sets, and you are asked, how big is the union of their union? And for now, we'll work with the simplifying assumption that these sets are pairwise disjoint. In other words, they are non-intersecting. Sorry, this is an awful symbol. What I meant is here is an empty set. I just see that it is rendered pretty badly, but this is an empty set notation. Okay. So in this case, the cardinality of a union is just a sum of the individual sets. It's not going to be true if these sets have non-trivial intersections. We will deal with this later. Okay, so for example, let's say we modify our lunch example, and now a lunch selection is as before, sandwich, side, and drink, but a drink now can be one of hot drinks or cold drinks. Okay, so but the basic thing to observe is that, okay, hot drinks and cold drinks are non-intersecting, right? So basically I can think of this as drinks, which is a union of the set of hot drinks and cold drinks, and it's just, the cardinality of this is just cardinality of hot and cold together. I mean, I'm over laboring this example because you can see immediately by yourself that, like, if that there is no repetitions here, and therefore the number of drinks is 5. Okay, but basically this rule applies because these two sets are non-intersecting, and so if this is the new rules for how we're making selections, the number of drinks have grown. It was 3 before, or right, and now it's 5, which changes the count of possible of all selections. Here is other examples types. So let's count passwords of a certain type. This is often enforced by websites to try to make passwords force people to choose passwords from large sets. Okay, so their passwords are not too short so that they cannot be easily searched through, right, and enumerated, because some attacks on password authentication will basically will depend on whether it is how fast one can enumerate over all possible passwords in that space. So let's see if certain ways of enforcing that there is going to be lots of passwords are, they work or not, and how are they influencing the password space, the size of in other words, the number of possible passwords of that type. So let's say that the password is a string of letters or digits of length 7. So this says that any string of 7 characters, each character is either a letter or a digit. It doesn't say that you have to have any digits. Perhaps each character is a letter, or vice versa. Perhaps each character is a digit, right? It just says that you're free to choose for every character, either letter or a digit. Well, so in other words, passwords are sequences in this set. These are sequences of 7 characters, and each character is either in D or in L. D is digits, L is letters. So the answer is the cardinality of this set, right? Because it's a Cartesian product, so we just take the cardinality of D union L and take it to the 7th power. But because D and L are non-intersecting, right? So digits and letters are separate. The cardinality of this is just a sum of possible digits and possible letters. Okay, so let's say there's 26 English letters, so the second one is cardinality 26 and the first one cardinality 10, and so this is the answer. So so what is the process of choice, right? For every character, you basically use the sum rule, either digit or a letter, and they are not intersecting, the digits or letters. And you make that choice independently 7 times. So the high top choice is product rule. And yeah, well, yeah, so basically, no, the choices are like you go down every time you choose an element of the sequence. And what is the forking? It's 36, 10 for digits, 26 for letters, and at every point in this tree of choices, you have 36 factor of increase, right? Hence, this is the final answer. Okay, let's say we modify this constraint and say, I want you to count passwords which are strings of letters or digits of length 7, as before, but they must start with a letter. Okay. So can you see this as a sequence of 7 characters? Each of the characters must be in a certain set. Well, the 6 characters are in these sets because they're unconstrained. They can be either digit or letter, but the first character is a letter. So in other words, the sequence that describes a password is the first element is a letter, and the remaining 6 are chosen, are each characters in this set. Right? So the final answer is just that. How about we say that the password is as before, so made of digits and letters, but it has length 6, 7, or 8. Okay, so you can have a 6-element string, 7-element string, or 8-element string. Well, this is the set of all possible passwords. You either have a 6-element string over this alphabet, or a 7-element string, or an 8-element string. And because clearly these things are distinct, right? Because this is a set of 6-element strings and this is a set of 7-element strings, so they cannot be confused. The cardinality of the union is cardinality of each of these components because there is nothing in common between them. Okay, they're over the same alphabet, but these are strings of different length. These are strings of length 6, these are strings of length 7, these are strings of length 8. So you add them independently and you apply the same rule as before to each one to get that the total is 36 to 6, plus 36 to 7, plus 36 to 8, right? So, or you can think of this process of choice as at the beginning you fork between 3 independent things, like you choose the size, either 6 or 7 or 8. And you do the same process as you did in the previous slide for each of them. But the total number of leaves on the bottom is the sum of the first tree leaves, the sum of the leaves of the second tree, and the sum of the leaf of the third tree, because these were basically the top choice forked between these three trees. Some more examples. So say that you have the set that I'm looking for is the set of hold on a second, I lost slides because I'm trying to make it so that to see the okay, good. Sorry about that. So the set is of binary strings of length 10, but they have a constraint that the first and last bits are the same. In other words, this, for example, bit string is in the set, but this one is not because the last and the first bit are different. Okay, so okay, so send your votes. What's the cardinality of the set? How many bit strings of length 10 there are whose first and last bits are the same? That's the only constraint. You can have an arbitrary bit string. The only constraint is that the last bit is a copy of the first.
But it has to be length 10, right? Because there's a total of only two possible
Yes, length 10, right here. Yeah. Yes, that's length 10. Okay, so yes, it is set B, right? And that's because well, it's a think of this as a product rule. Okay, you're making choices for each of these indices separately, except when, so you have two choices for first, two choices for the second, two choices for the third, etc., until you get to the 9th. But then for the 10th, you have no choice. It has to be a copy of the first. So there's no choices at the last digit. That's why it's this one. Okay. But you can think of this, okay, so it's a particular way of going through it, this example, but there is something more fundamental going on. We call this a bijection rule. So say you have an set whose it's hard for you to count, like you're not sure how to count, but you map this set into another one, and you map it using a bijection. So now you know that if there is a bijection between set X and set Y, then they must have the same number of elements, because otherwise there wouldn't be a bijection, right? A bijection gives you a one-to-one correspondence between everybody in set X and everybody in set Y, and moreover, everybody in set Y is covered. So it's invertible, right? The two sets are, that's actually a definition of two sets having the same cardinality, if there is a bijection between them. So the point of this is that perhaps the other set is easier to count. And so, so what was the bijection here? The bijection was between all elements in S10 to 9-bit strings, right? It's a bijection because the bijection says, take an element in S10 and just drop the last bit. You're getting a 9-bit string. Now, so it's a function from S10 to 9-bit strings. Is that function a bijection? Well, is there a collisions in it? So can you have two strings in here that if you drop the last bit, you are creating the same 9-bit string? Well, no, because the last bit is, basically carries no information, right? It's determined. So dropping the last bit, there's only one of these bits that you could drop, right? So it's because it's determined by the first bit. So it's does not have create collisions. And is every 9-bit string covered? Yes, right? Because you can write a bit string here, and that has arbitrary 9-digit bit string, and just copy the first bit. Actually, maybe it's easier to think of the bijection from all 9-bit strings to this set, right? That's in fact how we count it, precisely because of this bijection, right? The bijection takes 9-digit string and creates a 10-digit strings from it as follows: copies the 9 bits and then copies the first bit into the 10th position. Is it the bijection? Well, did it create any collisions? No. Did it cover everybody in here? Yes. Okay. So that's why the two sets have the same number of elements, right? So that's one example. Here's a different one. You have a set of n elements, and you're asked how many subsets of that set there are. Okay, so you have an n element set, does not matter what those n elements are, and you were asked count the possible subsets. Well, you might already know the answer, because like this was an example of a recursive algorithm that was, I believe, on a homework to enumerate all all subsets, right? And there were 2 to the n of them. Well, here is another way to convince yourself that there are 2 to the n subsets, right? So there was a proof in this recursive code that it's correct. So you can basically use this proof to also show that that's indeed true. And so, you know, we were told from the very beginning, like when we introduced subsets, this power set, right? That, well, you can count the number, this power set cardinality by taking 2 to the power cardinality of the set X. Okay, but let's see now why that is true. So one way of thinking this is true is to say, okay, let's come up with a bijection within all subsets and bit strings of length n. Now, if I had this bijection, then I would know that the cardinality of set of subsets of X and set of bit strings of length n is the same. Otherwise, there couldn't be a bijection between these two sets. And I know what's the cardinality of the set, right? It's 2 to the n. So then I would get convinced that number of subsets is also 2 to the n. What is this bijection? Well, here is a bijection. For every subset, I will map it to a bit string such that if the ith element of X is in this subset, then the ith bit of this bit string is 1. These bit strings are called characteristic of a subset. Whenever 1 appears, the corresponding element of the set is included in a subset. So for example, this character, it corresponds to, let's take X, let's call this element not X1, X2, X3, but A, B, C, D, E, F, G, right? So I have 7 characters, 7 elements set X, and so I will represent subsets by bit strings of length 7. The first bit will tell me, is A included in the subset? The second bit, is B included in the subset? And so on and so forth, right? And so, for example, this bit string represents this set, right? A subset A, B, and F. And if I flip the last bit from 0 to 1, that means that it's the same set, but also G is added, right? Because the indicator bit for the corresponding character, which was G, got flipped from 0, which means G is not, to 1, which means G is included, right? So in other words, these bit strings are representations of subsets, and they're unique representations. So every subset will map to a different bit string, right? Because if you take or not take an element, it's a 0 or 1 in a corresponding position. So these two different subsets must have correspond to two different bit strings. Also, it's an onto mapping. So every bit string is mapped by some subset, right? If you want, you can think of this bijection in the opposite direction. It doesn't really matter. Whether you think of bijection from X to Y, or whether you're thinking of its inverse from Y to X, it doesn't matter. The point is either this bijection or that bijection, and what are those two bijections? Are inverses of each other, right? I don't care which bijection you think about. Either one will tell you that these two sets have the same number of elements, right? So perhaps going the other direction is easier. I give you a bit string, and you can read off what the subset is by interpreting these bits as decisions whether or not the first element is in the subset or not. This bit tells you the second element and so forth, right? Okay. So here's another example of a bijection rule in usage. So let's say you're asked to count 6-bit palindromes. They are bit strings. Okay, so the strings are composed just of bits. There are 6 bits, but there is a constraint that it's a palindrome. So if you read the bit string from left to right, and you read it from right to left, they're identical. Well, okay, how do you count? There's a bijection from 3-bit strings to the palindromes. This bijection is super easy. Take a 3-bit string and concatenate it with its in reverse, right? So just reverse of X is the same bit string, but in the other direction, right? Reversed order. And this is a bijection between these two sets, because every palindrome has this form. For some X, it is of the form X followed by X reverse for some X, which has 3 bits. And there is no collision in this representation, right? In this mapping. So a unique 3-digit string will give you a unique palindrome. So the two sets have the same number of elements, right? So the answer is 2 to 3, right? You can also think of this as a generalization of this earlier example, which I was telling you, like 9 bits followed by a 10th, which is a copy of the first. Well, so this is a string of 3 bits followed by copies of these bits, just copied into different position, right? So the last one, yeah, so they're just copied like this. So it's really the same example in some sense.
Professor, what if the string is length of 5?
Yeah, that's a great example for an exercise, right? So what would this bijection be at this moment? I mean, how much freedom you have, and where does the freedom end? And now from then on you have copies, right? So what's your guess? So if there's an n long palindrome and n is odd, how many free choices of bits you have?
N plus 1 over 2.
Exactly.
Okay.
Exactly. Okay. So so here's okay. So in this, okay, well, actually I went over this, right? So what is the this bijection from 9-bit strings to S10 is this one, right? So I just take my bit string and I attach a copy of the first bit at the end, right? So I've already covered this example. Well, here's another. So bijection is one way to count, right? If you have some tricky set, but you found the bijection, you basically do the sets that you can count. You've solved the counting problem of your original set. What if these correspondence, you don't have a easy bijection, but you have a function that is regular in the way that bijection, for every argument, it gives a single. It maps to a single value. Right, sorry, it always maps to a single value. The point is that every, okay, you know what, before I start hand waving, let's give an example. So let's say you could count shoes at a party of children, and they all had to take off their shoes. And can you use it to count the kids? Yeah, yes, right? You count the shoes, they're all in a pile because the children are messy. And you just count all the shoes, you divide by 2, and you know how many kids there are. So this is an example of a 2-to-1 rule. You counted kids by counting shoes instead. And by knowing this correspondence, that roughly 2 shoes correspond to a kid. In general, you have 2 sets and some function correspondence between them. But this function is not the bijection, but it has certain regularity. Namely, let f-1 of y denote the set of pre-images of y. In this shoes to kids case, the pre-image of any kid is the 2 shoes that corresponded to that kid, right? So if I map shoes to kids, the pre-image is the set of shoes that mapped to a given kid. And it's k-to-1 if the number of pre-images of every value is fixed. It's always some constant k. In this case, k was 2. The set of pre-images was 2. Because these are pre-images, so pre-images of two values in the range cannot intersect, right? Because that would mean that the function maps the same argument to 2 different values, so they cannot intersect. And also, the pre-images sets are not intersecting, and they also partition the space, right? Because every value has, every argument is mapped to some value. So therefore, if you take all the pre-images, they're going to fill up the argument space X. And the partition, moreover, has this regularity that each pre-image set has exactly k elements. So now you can tell, if you can count X, then you can count Y. The relation is this one between them, right? So either way, if you don't know how to count Y, but you can count X, this relation is useful. Or if you know, vice versa, right? This relation is useful. It's a generalization of the bijection rule. Instead of 1-to-1 correspondence, you have k-to-1 correspondence. And it will be helpful either direction you make it. So I can represent this this problem, the same problem of S10, which is bit strings whose first and last bits are the same, in this fashion, if I want, right? It's a 2-to-1 correspondence. It's this one. Okay, it's a little contrived. So I take you see, instead of, there is a bijection between S10 and 9-digit strings. But maybe it's slightly perversely, but I can also think of this as a function that takes any 10-digit string and creates that one. And what that function does is that it like slashes the last bit by making the last bit really a copy of the first. That slashing is a 2-to-1 operation because basically it ignores the last bit, right? So two possibilities were mapped into the same, right? So that function is a 2-to-1 function, and this number of elements here is 2 to the 10, and because it's a 2-to-1 function, I take 2 to the 10 over 2, and I get the number of elements here, which is 2 to the 9, right? Which I just counted using the bijection rule by looking at 9-digit strings. But I can squeeze my eyes and think of this as a case of a 2-to-1 rule.
But how do you define a 2-to-1 function from that set of binary strings? It's like how do you know that, how do you know it was defined like that? Because like you said, this is
you don't. This is they're not defined by anyone. You define them. You know, you can think of them in any way. Like I'm giving you examples. Like if you think of this function, then it's a case of 2-to-1. If you think of a previous function, then it's a case of a bijection. Okay. Any way you think of a given counting problem, you might cast it in this way, you might cast it in that way, whatever is helpful. All I'm giving you is examples. Here is the function that worked. Okay. For any example, you have to come up with some way that works, right? So the good, you know, what can you do? You look at the, you know, the Zybook exercises and stuff, you know, gives you like, okay, here is a possible application. It is like these sequences, or it is like there is some sort of K-to-1 rule for counting these. The more you do them, the more you will see patterns, and the more you will be able to apply it to some, okay, here is a counting problem. Now you're free to choose some way to count it. Okay.
Could you please explain the function?
Yeah, so, you know, this is kind of a contrived example. The function here takes the 10 bits.
I use
and
shorter
the argument X is a 10-bit string, and it does the following. It forgets the 10th bit, and instead it creates the value is the first 9 bits, the 10th is forgotten, and instead replaced by the copy of the first bit in the string. Okay, so you took this bit string X, you slashed out the X10, the last bit, and the value here is the first 9 bits and a copy of the first. That function is 2-to-1. Okay, because basically it has exactly 2 collisions at every value. The 2 collisions were corresponded to this last bit being either 0 or 1, because it was forgotten by the function, right? So you just threw out that last bit, so that exactly creates a collision.
Does that overlap? Could you please give a shorter example, like length of 5 and how to do this?
Wait, it doesn't matter what this length is, right? Whether this 10 here, you know, it's exactly the same if it was 5 to S5.
Yeah.
Like
1, 1, 1, 2, 0.
You know what? We will so we will find these K-to-1 examples later on, right? So like if you're not super happy with this example, there will be other examples.
Okay.
You know, the example with kids and shoes is another one right here. You can think of creating palindromes in this way, right? Like you take how many 8-digit palindromes there are. Take 8-digit string and just forget the last 4 bits, and instead of these thrown out bits, you take these 4 and you copy them, but in reverse. What kind of function is that? It's a 16-to-1 function, because basically all these bits were forgotten, meaning that no matter what these bits were, the value of the function is just determined by the first 4. So that means that all choices of these 4 digits that were forgotten by the function, they all create collisions. They all collide on the same value, right? And how many of them there are? 2 to the 4. So 16. So it's a 16-to-1 function. So I can count 8 digit strings, of which there are 2 to the 8, and slash out 2 to the 4. And 2 to the 16 divided by 2 to the 8 divided by 2 to the 4 is 2 to the 4. It's not a very natural way of counting, but it gives you the same number, right?
So this function is creating palindrome.
Say it again.
So this function is creating a palindrome for the binary.
Yeah, the one. Yes.
Oh,
yeah, that would be the one way of looking at palindromes. Okay. Okay. So far we have a sum rule was for counting elements of sets which are unions of other sets. So you have some possible choices of what you need to count, and the choices are either in A1 or in A2 or in A3, and these choices are disjoint. So for example, you are asked to count n-digit passwords for where n is either 4 or 5. Well, so it's number of 4-digit passwords plus the number of 5-digit passwords. That's an example of a sum rule. It's either of these 2 subsets. So A1 is this set, and A2 is this set, and they're non-intersecting. A product rule is if you're counting classes or objects who can be represented as sequences whose ith element is in set AI. And so, for example, 3-digit decimal password. So password is over the alphabet, where each character is a digit, not 10, right? In decimal. So how do you count possibility of 3-digit decimal numbers? You have to choose the first digit, the second, the third, and you choose them all independently, right? And bijection rule, if you find the correspondence between 2 sets, which is a bijection, then you can make known that the cardinality of these 2 sets are equal. And more generalizing this, if you find a function which is a k-to-1 function, so the preimages for every r value, the set of preimages is constant, and it's some constant k. It is a generalization, because for k equal 1, a k 1-to-1 function is a bijection, right? Using this definition. We also assume that this function is onto. Okay. Moving on, counting permutations. First, what's an r-permutation? R-permutation is a sequence of r items from a given set, but unlike general sequences that we dealt with a few slides before, right, using the product rule, there is a constraint that you cannot have repeats. In other words, let's say this is the set, which I used to call an alphabet before. And you have you have to count how many 4-element sequences there are, whose every element is in the set, but the sequences have the property that there is no repeats in these elements. In other words, once the first element is chosen, these elements are all chosen from a reduced set. The second element can be anything from here except this one. And the third element is chosen from even more reduced set. It's S, but with G and A kicked out. Okay. So that modifies the notion of how do you choose a sequence, right? From whose every character is an element of a set. Because unlike the previous thing where I used product rule, the elements, it was crucial that for the product rule that each of these characters is chosen independently. Like in the lunch schedule, you know, it doesn't matter what sandwich I took, the drink is completely independent, and it doesn't matter what sandwich and drink, the side is completely independent, right? And in all these examples, it was the case. But now I'm telling you, okay, let's count other objects, sequences, but with this constraint that their characters you choose cannot be chosen twice. That's called an r-permutation over a set. Okay, so, and the order matters. It's I'm going to call these two sequences different r-permutations, right? So if you think of them as sequences, then obviously these are two different sequences, right? So how many? So my definition of an r-permutation is a r-element sequence. Every element is in the set, but they don't repeat. Okay, so how do you count them? Well, here's a general formula. And you can think of this as some sort of generalization of the product rule. So you have to count r elements. The first element is unconstrained. It can be any of the element in this n element set. But once you choose this first element, the second one is now constrained. It's chosen from the reduced set. It's chosen from a set of effectively only n-1 elements. And so the first time the tree of four choices forks, it has n possibilities. And after that choice is made, the next forks has n-1 possibilities. And after that has n-2, and so forth. Clearly, you can see r cannot be longer than n, right? Because at each level down the path, you have one less choice. Once r is n, you have no choices, right? And why? Because the only way to make such a permutation is of size n is to choose every element. And once every element is in the permutation, then there is no possible, you cannot choose another element with no repeats, right? So this is this is therefore a natural formula, right? With like, if you going r times, the last choices will be this many, right? Because this was your first character choice, this is the second, this is the rth. And you can see also that this product has to satisfy this, right? So n factorial is all products from 1 to n. This is not all of them. You stop at this point, but that's like taking all and then subdividing the factorial to what's the first one missing, n-r, right? So you just divide them. So there is a special notation for this quantity, and it's denoted this way. It's a number of permutations of set of length of n elements, And the permutation is not all of them, it's R of them.
Order matters here, right?
Yes, because it's a sequence. So okay, so let's do some example.
So what does not matter in permutations? What was that did not matter? Just want to make sure if I didn't misunderstand anything. I know that order matters. Is there anything else that matters or that doesn't matter?
Well, yeah, I'm not sure. Yeah, it's a sequence of
Okay,
elements
just a second.
such that you cannot have repeats. So this sequence, each of these has to be different.
Okay.
That's the rule. Okay. So okay. So let's see how this works in some application. So let's say you are asked, there is 4 tasks and 20 computers, and how do you distribute these tasks? Okay. But there is no restrictions on the number of tasks a given computer can make. Okay, so there's 20 computers in the system. Let's say you're routing 4 messages, and these 20 computers are your connections, your routers, connections of UCI networks to the outside world. And how many ways these 4 messages could exit UCI? Well, and there is no constraints otherwise, right? So basically, how do you count? Well, each of these 4 messages basically have independently a choice of 20 routers that it can be routed through. So it's 20 for the first, 20 for the second, 20 for the third, it's 20 to the fourth. It's all possible choices. But let's say that because the tasks are independent, right? Like there is no constraint, like how the first task was done, how the first message was routed, does not influence how the second message can be routed, how the second task is done. But so in an event, it's like a 4-digit, it's a string of 4 characters. Each of them tells me which computer services the ith message. So the ith character tells me which computer serves the ith message, right? So it's a 4-digit strings over alphabet of 20 elements. Now, what if I give you a constraint that each computer can only do 1 message? So now you assign these 4 tasks, 4 messages to one of these 20 computers, but once you assign the first one, the others are chosen from a reduced set. You no longer can use this computer, the chosen one.
So one computer cannot
right?
2 tasks.
So it is an R permutation. It is like these other sequences, except that you choosing them from reduced set. What's your question?
So one computer cannot serve for 2 tasks.
Exactly. So this is the modified formula, right? You have 20 choices for the first, but only 19 for the second, and only 18 for the next, and so forth. It goes down, and in other words, it's a number of 4 permutations over this alphabet. So 4-element sequences of characters from a set of 20, but no repeats. You cannot have the same character twice. Okay, so good. Let's another example. So say you have 3 kids and they select from a bin with 30 prices. and how many ways they can do so, right? So 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 then you have to think, okay, am I thinking is every selection a sequence of kids? Am I assigning prizes to kids? Am I assigning kids to prizes? Right. Well, but here's one way to look at it. Each outcome, each selection is a 3-element sequence. First element is the prize that Larry got, first kid. The second element is the prize that Curly got. And the third is the prize that Mo got, right? So it's 3 characters. And first one is unconstrained. It can be anything from the set of 30. But once that prize is given, right, the second character is constrained. It cannot be the same as the first one because the same prize couldn't be gotten by 2 different kids. So if you think of this way, it's a set of 3 permutations, so sequences of length 3 out of set of 30 elements with no repeats, right? So it's this 30 times 29 times 28. And you can come up with the same number, possibly looking at this differently. But some of these ways might not be productive, right? So you might sort of start thinking, okay, I'm going to assign, have a function that will represent this process in some other way. And I cannot come up with this on the go, but some way of these assignments might not be good. They have collisions, they overrepresent, or they don't cover everything. And if you have a problem, try to switch the way you're thinking of who is being selected, how to represent this counting problem.
Professor,
Mm-hmm.
you could represent this as 30 factorial over 27 factorial as well, right?
Well, because that's an identical thing, right?
Yeah.
I mean, this is 30 factorial over 27 factorial.
Okay.
Yeah. So this was the question. If okay, but what if there is no restriction on the number of prizes a single student gets? Okay, so you have 3 prizes and 100 students. So we're flipping, right? Like in the example before, there's 3 prizes and 30 prizes, sorry, and 3 students, or 3 kids who are drawing. These prizes are, and now I have a tiny set of prizes and a large set of people who potentially get them. So obviously not all of them will get it, right? In the previous example, every kid was guaranteed something. And what if there is 100 students and 3 prizes, and there is no restriction? So these 3 prizes are for something completely different, like the best test taker, the best homework writer, and the best Piazza participant who answered most questions. Okay. Could be independent, could be dependent, right? Like there's no constraints. It could be the same person who gets all 3. How many possible assignments are there?
100 cubed.
100 what?
100 to the 3 power.
100 to the 3. Yes, right? Because it's a 3-character sequence. Each character, first character says who got the first prize, second who got the second, third who got the third, and each is independently chosen from an alphabet of 100. Now, if I modify it so that the prices are dependent, like for example, it's just first, second, and third, best score total. So the same student cannot be first, second, and third, right? Like there's gonna be, each of them will go to a separate student. And now what is it?
100 factorial over 97 factorial.
Exactly, right? So it's a 3-element permutation out of a 100-element set. So 3 permutations. So exactly. So 100 factorial over 96 factorial. Okay. So in general, there is a general concept of permutation, not r-permutation, but it's actually a restricted concept. It's what happens when r equals n, right? So if you have an element set and you take a sequence that includes all of them, so it's a sequence of length n, and the order is the only thing that matters, right? Because you already know that you have to take all of them. So if you think of it as a set, it's not interesting. You took this whole set, so there's like only one choice. But the whole choice is in the order, right? It's basically a permutation is an ordering. You have an element. How many ways there are to order them? Okay, and it's the case of r equal n. So if the general formula is n factorial over n minus r factorial, this applies here too, because n minus r is 0 and 0 factorial is 1. So the number of permutations of a 5-element set is 5 factorial, right? And but here are some examples of slightly tricky problems that can be cast in this way. And whereas okay, how many ways to order this element there are? It's 5 factorial because you have to choose one of them as first, 5 choices, one of them, the remaining ones, as second, so there will be 4 choices, etc. Right? And the number of choices decrease, it's going to be all these integers multiplied, right? Consecutive integers multiplied. But what if I give you what's this constraint? That I'm looking at all orderings, but with the constraint that B and E are next to each other.
S minus 1 factorial times 2.
The 1 factorial is just 1. No.
I mean S minus 1 factorial.
S is a set.
Oh, the cardinality of S minus 1 factorial.
And why?
Because I can think of B and E as one single element and the permutation there.
That's exactly right.
The cases.
And there's 2 cases corresponding to?
Yeah.
Corresponding to what?
BE and the EB.
Right. And the last bit of freedom is to choose the order of E and B. Right? Exactly. So there will be 2 of these, depending on how do you order B and E. Exactly. So I can think of this as the number of permutations over this set, where B and E are in this order, and permutation over this set, right? And these are non-intersecting because every string here will have BE at some fragment, and every string here, none will have BE, right? And vice versa, right? So these 2 sets are non-intersecting. You have basically split this as a sum rule of 2 different classes, each of which can be computed using as a permutation. And if I change this, so I say that B must come before E and immediately so, well, then I reduce it to this case, right? But what if I what if I had that B must come before E, but not necessarily immediately before? Right, so if they are joint, if they're basically co-joint, right, then okay, then I just think of this as a smaller set where this tuple is a single character.
I have a question about that because, like, if I remember clearly, because like when you were talking about the permutations in which B comes before E, but not necessarily immediately before E, like, does that so that could that be like in the set like AB, BA, or BB, and then CB, and then DB and BD? Is that the combination?
Wait. This is a question to you.
Okay.
I haven't been talking about this. Like, this is a question to you. Well, how can I count the set, right? So I'm modifying my constraint. You already know how to do when B and E must be immediately next to each other. But what if you're told that it's any permutation, but with the constraints that B is somewhere before E? How could you count these?
Five factorial over 2.
And why?
I can first randomly permutation 5 elements, and there are half cases that B is in before E and E before E.
You mean 4 factorial?
No, he means 5 factorial.
Yeah.
I know, but like 5 factorial over 4 factorial, because like there's 4.
No, 5 factorial over 2.
Yeah.
Okay, and say again why?
I first ignore the restriction. I just randomly permutation 5 elements.
Good.
And I thought there are half cases that include B comes before E.
Yes. And why do you think that exactly half? This will make exactly half, right? So you say, okay, I'm going to call all of them, and I'm just going to say that the number of those where B comes before E is exactly half. So I can count all of them and just divide by 2. But why is it that it's exactly half? Huh?
For any permutation, there are 2 cases, B before E and E before B.
And why are these 2 cases the same number of both?
I can switch them, create a function, and find the bijection between them.
Yes, yeah. Yes, exactly. This is a case of, well, you can think of this again in 2 different ways. So let's think of this as a 2-to-1 rule. Let's think of this as a 2-to-1 rule. Like, right, it's a function that takes a yeah. So where's the bijection?
So for all
2-to-1, yeah. So take a permutation. Here is the function from permutations to permutations where B comes before E, right? So all permutations. This is my argument set. Permutations where B and E, B is always before E. This is my value set. And the function will do the following. We'll take the permutation and we'll do the following check. If B is already before E in the permutation, I leave it as is. But if E is before B, right, then I flip them. That's my function. Now, that function is 2-to-1 because it can create a collision in one way only, right? Everybody but B and E are unmoved by this function, and B and E could be moved but either they are in the correct order or they're flipped, in which case you create a collision. So the number of pre-images for any element, right, is 2. It's exactly 2. Is this value that you take a permutation where B comes before E. And what are its pre-images? Well, that same permutation, first of all, will be mapped, plus its sister permutation, which is the same one, but with B and E switched. That is the 2-to-1 function. Is everybody covered by this function? Yes. Every permutation is going to be there with this constraint, right? It's going to be created. And how many collisions? Exactly 2. That is a beautiful case of 2-to-1, right? So if you thought that the previous example is contrived, boom, you have a beautiful example now. Yeah. Okay. Any? Yes. So the slide is all permutation, and B is those with B before E, and I'm not spelling out this function here, but you can reconstruct it, right? It's the permutation. It's the function f either leaves B and E, leaves everything if B and E are already ordered correctly, or it flips B and E if they're not ordered correctly. Okay, so I think this is a good place to stop, right? Because in the next segment we're counting sets, and so far we've been counting sequences, right? So if you basically go to this very general thing, what we have basically done is we have generalized this case, looked at like what about sequences where they all these sets are the same, except that this guy now is a constraint. It cannot take, there cannot be repeats between these elements, right? We will build on this next week, basically. So let me move to questions now, especially if there are some about homework or test. So we'll revisit this counting. I will release some homework about it, and we'll revisit. We'll start next week. But on Thursday there is a test from all the modular arithmetic stuff.
Did we go over the RSA and encryption, or that was a separate lecture that you did from the side with that YouTube video when you were talking about Euler's theorem?
What's your question?
So that video, was that recorded like some other time, not during the lecture time when it was talking about the Euler's theorem, right? Lecture 12B, right?
Yes.
Okay, so with the Euler's theorem, is it just proving C and M? You know how when you get the encrypted message and how they're inversely related to each other, C and M?
I also posted some slides from this. I think I just posted them earlier today, so I didn't broadcast it on Piazza. I can, let me just hold on. I'll share these slides with you. Okay, and okay. Hold on a second. I'll share this. Do you have RSA now on the screen?
Yes, I see it.
Oh, okay. So these are the slides I included on the website now. They have some extras, so I'm explaining the extras in case somebody. First of all, people want to know, is this all included on the test? And so that's why I'm going over like, no, this is an extra, this is an extra. But in particular, there are slides that just go over RSA. One more time. So here's the crypto system.
Did you say the material today is not on the test, but RSA is, right? Correct?
Correct.
Uh-huh.
So the encryption function is you take a message and the key E, and you encrypt by taking M to the E, and you decrypt by taking C to the D. By the way, this is also important stuff. So when people talk about RSA security, they say, okay, factoring has to be hard. And why is that? Because N is the public key, modulus N, right? So if factoring problem was easy, if it was possible to quickly factorize N, then you would get these two primes, P and Q, right? The person who factorizes gets the P and Q. And if they get P and Q, then they can compute phi, which is P minus 1 times Q minus 1. And if they compute phi, then given the public key, they can, on their own, compute this multiplicative inverse, right? The D is just E, multiplicative inverse of E mod phi. They have E in the public key, and they have phi if they factorize N. So they would be able to compute the private key. So that's why factoring must be hard for RSA to be secure. Okay.
So
that's an important thing that I haven't quite spelled out in the online lecture. But okay, so here's how you encrypt, and now this is what you were asking. I mean, so it's Euler's theorem says that this is the fundamental equation when you are exponentiating mod n. And why am I interested in it? Because encryption is exponentiation mod n, and decryption is an exponentiation on n, mod n. So I want to know how this sequence of encrypting and then decrypting mod n will. My basic question is, if I encrypt M and then I decrypt the resulting ciphertext, do I get the same M back? And that I do will follow from the following. It's Euler's theorem that if you are exponentiating mod n, then once the exponent reaches phi of n, it's as if it was a 0. So if you remember exponentiating mod small moduli, right, in this first homework, you notice that at some point you always get back to 1. So you take any number, mod 7, you exponentiate it over and over and over. Eventually you get 1 back and you cycle, right? Because the next power will be identical to this first element, and so forth. You're gonna cycle. What Euler's theorem says is that at phi of n, there's always a cycle, where phi of n is a number of elements in Cn which are coprime with n. So for the case of RSA moduli, it's this number, right? And the consequence of Euler's theorem is that if you exponentiate m to something, call it x, in fact, you only can exponentiate it with x mod phi, because m to the phi is like as if it's m to the 0, because it's a 1. And I think in the online lecture I'm actually explaining this fact a little more. So this is okay, but here we go. So just observe the following. If you if C is m to the e, right? C is properly encrypted m. Then if you decrypt it, so you take it to the D mod n, well, this thing is equal to that thing, right? Because C is m to the e, and everything is going to be mod n. So I'm not going to repeat mod n, mod n, mod n, everything. Like all these equations, just hold mod n. So the decryption is really m to the e to the d. So that's the same as m to the e and d multiplied. But by Euler's theorem, if I'm exponentiating to something, my x is e times d, whatever integer that is. I can reduce this integer mod phi, and I'm going to have the same answer. So I can replace m to the ed with m to the ed mod phi. And ed is chosen in this way to exactly guarantee this, because ed is chosen in such a way that they are inverses of each other modulo phi, which is this equation, that ed mod phi is 1. That's how e and d are chosen, right? It's right here. Okay, that's the private key equation for RSA. Given exponent e, which is public, d is computed to fit this equation. And that's always possible because e and phi are coprime. So this d always exists. The multiplicative inverse exists. Okay, and can be computed with extended Euclidean algorithm. So this is the constraint between the private and the public key. And this constraint kicks in right here. It basically guarantees that m to this is the same as m to 1. And therefore it's just m. So this whole chain of reasoning argues why an RSA encryption is correct. So if you encrypt and decrypt, you always get the same thing. Is that what you wanted me to go over?
Yes. So then all we just need to know is that you could switch the position of you could switch you could put in m as whatever the decrypted message was, m to the power of e mod n to the power of d, because that's what c equals in order to get your encrypted message.
C is m to the e.
C is m to the e mod n. Right. So then in order to get your message like retrieved back, you can what you could do is because I'm on the valid because I'm on in the textbook proof 9.9.1 validity of the RSA crypto system. Is that where Euler's theorem is? Euler's theorem. Why do I keep forgetting how to pronounce?
No, well, that's fine. So yes, that's exactly what I'm saying, right? And it's also in this online lecture. I'm going over that as well. So this is the same thing.
Okay.
Yes, it's just the same. Yes, it's a reasoning why RSA, when I decrypt, is the inverse of encryption.
Could I use that for the last problem in the homework, 9.94, using Euler's theorem?
I'm not sure you have to refer to it, but yeah, well, if you need to, then sure. So just on the slides that are placed from the same lecture, there is some more examples covered, right? So just flashing it. So so some particular example of okay, so let's now take primes and let's create the public key and e and d, and then let's encrypt something and let's decrypt something, decrypt the result and see that it's equal, right? So you have one more example on the slides.
Hi, Professor.
Are
we required to prove or design a recursive algorithm for some of algorithm?
Oh, on the test?
Yeah. I thought it was last test content.
No, yes. So well, okay. So here's where the recursion came in this in the new segment, right? So there was one recursion was in the representation by when you convert digits from when you take an integer and you want to cast it as a base B integer for whatever base, binary, hex, arbitrary. The algorithm for doing that is very simple recursive algorithm. Okay, so that's a recursive algorithm. Fast exponentiation, recursive algorithm. And GCD, recursive algorithm. So at least 3 places you had recursion in this new topic segment, right? I might be forgetting like some other place where we had recursion, but it's like right on the top. You had 3 times that recursion happened. So
we need to verify it on test.
What do you say it again?
Do we need to verify any of these recursive algorithms on the test or prove it?
No, but you have to understand that they work, right? Because so I mean, a typical question is like here is a integer and represented base 7. Okay, so you have to run this algorithm, so you have to know how this works, and it's a recursive algorithm. Or well, you're supposed to know how Euclidean algorithm works and how fast exponentiation works. So here's the question, like, you know, just run the fast exponentiation to compute something. So you have to know how this algorithm works. I mean, but yes, but asking to prove, well, probably not.
So you only need to.
Moreover, it's a kind of I cannot really ask this question. You know why? Because the proof is in the book. So what does that test? You know, your ability to find the proof in the book and to copy it.
Oh yeah, that makes sense.
Yeah, but I mean, yes, I haven't made the test questions, but yeah, I don't think that there will be a proof.
So the homework question will be similar to the test, like previous test?
Yeah, it's always like that, right? So at least in my mind, these are similar, and by doing this homework stuff, you that's exactly what I'm testing you on, you know, on your comfort and an understanding of the stuff. But yeah, but, so I yes, but in I think with this class of material, like you know, I'm telling you, okay, so compute, you know, show me how do you compute a GCD. Yeah, it's precisely the stuff that you've been doing, right?
So we don't have to do the method as the same as the guidebook did.
Say this again.
I find another way to compute the prime number or another thing. So the format is quite different from the guidebook, but we get the same solution. Is that okay for do it on the test?
Compute a prime number?
Yeah, but another different form. I didn't use the symbol of modular or division algorithm.
I think you were thinking of some other example, because there's no such thing as compute a prime number. You know, choose a prime number. So no, I think you mean like
Finding GCD. Oh, sorry.
Exponentiation, right? Like modular exponentiation.
Yeah.
Yeah, so I sort of, I mean, there were several versions of this fast exponentiation algorithm. I gave one, a recursive one in lecture, and then an iterative one, which is a version of the recursive. Then the book has yet another iterative algorithm, and they actually differ. The book one goes from least, I think most significant bit to least, and I'm going from least to most. So for example, you can compute any way.
As long as we get the same the correct answer.
You're right, but the thing is that you have to follow some algorithms that make sense.
And I can explain that.
You have to.
That's fine. Okay.
Otherwise, it's a complete mess that this cannot be understandable,
Yeah.
right? So if you do some computations and some answer drops out, and we have no idea what are you doing, we're not going to grade it great.
Unless I explain that.
You have to explain something like, you know, here's what I'm doing, you know.
Okay.
Yeah, it cannot be just like a sheet full of like some stuff and then like an answer at the end, and we have no way of placing what it is that you're saying to anything.
So can I explain it later? I should explain it write it down on test or on grade scope after.
I mean, whatever algorithm you're following, I think that they are pretty simple, these algorithms, right? Like they tend to have 2-3 lines.
I find there are many steps in finding GCD of two large prime number. And
but the algorithm is simple, right? Like it might execute recursively or whatever, right? So, yeah, so how much detail do you write? Well, it's sort of, I know, there is limited time. You have to basically make a judgment as to, is this understandable or not? I think that for example, for GCD algorithm, well, you can explain it like, you know, my initial pair is 257, 39, and then my next one is 39 and whatever, because and the next one is like, you can write it briefly. You don't have to be very verbose in this. Indeed, you won't have time to be verbose.
So in finding GCD, can I just write down the sequence for the modular outcome? Like,
yes, but no, sequence is one thing, but like, I mean, you shouldn't, because you should write equations, because otherwise you have no idea whether this is correct.
Oh, I can't
yes,
do
so
it.
just a sequence, like, okay. Oh, my algorithm just went 259, 77, 27, 13. I mean, I cannot make head of tail. Like, why?
Because I do.
But if you write, okay, it's 239, whatever, next sequence is because this mod that is equal to this.
Oh, okay.
Okay, so that suffices.
It's clear now. Thank you.
Yes. Yes, and the thing, yeah, so, you know, if you don't write, then number one, if you make a mistake, there's no way to give you any partial credit, right? Because you made a mistake, we don't understand what you're doing, we have no idea, like, do you understand anything at all, or this is just some random sequence that came out. So you have to write, or otherwise, you know, then we can see, oh, you made a small arithmetic mistake here, the rest is perfectly sensible. That's different. Yes, so whether you explain or not is like heaven and earth when you make a small mistake somewhere. The guy who didn't explain gets close to 0, and the guy who explained gets close to full. So that's a huge difference there, right? And also, I don't see how you can write this stuff and be like relatively confident that what you have written is correct unless you write things down. And the third one is that, you know, we have, I mean, it is even correct, but there's no explanations, and we think that you're not doing this independently. You just copied it from somebody, emailed it to you. So these are the reasons why you should, you know, write it with some explanations. Okay. Okay.
How much work do we have to show for the homework?
For the homework,
Yes.
not much. I mean, I'm telling it to Son Piazza, like you can just give us final answer. We're not gonna check it much anyway. The
Okay.
whole point is for you to know how to do this stuff. But on the test, you definitely have to explain.
Okay.
The homework question is time consuming for the process of the last question.
Yeah, it's a lot, very time consuming.
With that kind of question on test, that would be no, there will definitely be. You have it like in the bank. So there will be exactly that kind of question. There will be like, here's RSA, here's the prime. Tell me, what is the public key and run what is the private key? How do you encrypt? The thing is that I'm just going to pick some smaller numbers.
Oh, okay. That would be easier.
Right. But yes, so that this is not too complex. Yeah. Yeah, but on the homework, it's not such a, like here, this is an example. It's pretty annoying, to compute this sequence, right? But that's because the numbers are quite large, right? So I'll pick some smaller arithmetics so that these computations are not so long and not so, they just take fewer steps, and the steps are easier. Are you all good?
Yes.
All right. Okay. And I will be asking the TAs to go, through overview of stuff tomorrow, obviously. So try to do like one more example of everything, basically. And if people have questions about something in particular, you can also use the time to clarify something.
Hi, Professor.
I
find a not very standard way to transfer the decimal number to binary string, like
decimal to binary.
Yeah, like let me share the screen. I find another not very standard way, but it works. And can I use that on the homework?
On the test or on the homework?
Both.
Yeah, so, well, on the test is, on the homework, you can do whatever you want. On the test, it's just that if you do something non-standard and it's not explained, I mean, look, when you convert decimal to binary, you can,
I found my
you
way
can basically verify.
Faster?
You verify fast, right? So, right, because the other direction is faster.
Yeah.
So,
if I give
probably
explanation,
verify. I mean, especially on the test, right? You would want to verify, right? It's like you're not gonna give a bit string, whatever your algorithm created, without verifying that this particular sum of powers of 2 really gives you the number, right? So you're going to verify this. Yeah.
So that doesn't matter for how the method get the binary string. As long as I get
probably doesn't.
Okay.
Yes. This algorithm, yes, for the binary string. So it's not a great test question because verification is so much easier. Then how did you do the mechanics of the algorithm to get to this answer is not really, if I give you short enough number, so I can either give you a very long number, and that's crazy because like it takes a long time to go through the algorithm. So people who basically guess the answer and then right, or by sort of match yeah, so it's not a good test question doing this algorithm from decimal to binary.
So
Oh,
like, can I use this way?
Oh, I cannot see anything.
How about now?
But
So
you are following the same algorithm, man.
Yeah, but it's faster and less mod number left.
It's the exact same algorithm. That's what I see.
But I find it's faster. I don't write down any mod, not things like.
Well, so yes, so that is one of the algorithms. So
it's not a formal way.
Yes, but as a trace of the algorithm, it suffices.
So it's correct.
Wait, so it's 217. Wait, 217 is your input?
Yeah, and I want to find its binary string. So I divide by 2, I got 18 and 1 remainder, and so on. So I reverse it, it will be 100 from bottom to top. And I got a binary string.
So, and where did you write your answer?
It's a draft for the homework. I wrote it on I just wrote the answer.
And did you verify it?
Yeah, it is correct.
Well, yeah, so, if that's your trace and you verify it, then that's it.
I can write down it on test, right?
Yes.
Okay.
Yeah. All right. But yeah, so basically, I mean, you will be following one of these algorithms. You will write down the intermediary results. You don't have to be very formal out of them, but it has to be clear to us, like which algorithm you're following it. If you're following some reasonable algorithm and we don't understand it, there's regrades, and you can say, okay, here's the algorithm I followed, and here's its trace. So
that's fine. Thank you.
That's fine too. Okay, so I'll see you later. Take care. Bye now.
Wait, so I don't have to show any work for the homework. I can just like write the answer straight.
Correct.
Okay,
yes.
Thanks.
Yes.